All right, so I wanted to make a video about the Intel Jordan Creek or C114 controller. Um, this is a video I've been struggling with for a while on multiple fronts, and it's again, it's really more for me than anybody else because this is a bit of old, obscure technology, but I feel like it's interesting enough to cover it nonetheless. So, a little bit of background on what it is and, like what I see, peering back into the past as kind of the target market for it. And then from there, we'll look into a little bit more on kind of a visual on how a layperson sees what it's doing, and then talk a little bit about again just kind of the interesting aspects of this product. This is not in any way a super deep dive into how it works and you know control gates and everything else that's in there. This is a very high level discussion on this, and I will also preface this by saying, I am only experienced in this insofar as what I have touched and worked on. So do not take this as, definitive or in any way uh, a set in stone way of looking at this. There are tons of engineers and stuff that I'm sure would be very offended by some of the stuff I'm going to say because I'm going to overgeneralize and do stuff like that. But again, this is really designed as kind of a high level overlook on what it is and why I think it's interesting. So, with that said, let's dive into it a little bit more and kind of set the scale and timeline for what we're looking at. And to me, this is really about uh, Intel's heyday. Intel's had several heydays over the years, but to me, this was one of those times where Intel was, they had more money than they knew what to do with, in all honesty. Intel had become a filter feeder, and Intel was going after any slice of market that they could get their hands on because they had saturated all of the primary markets. Again, to set the scale, this is before AMD really released Zen 1. And so what you're looking at is Intel in a market where AMD has not produced a real, and I'm going to put that in air quotes, server part in a very long time. Intel's server market share is, again, as close to 100% as you can realistically get. And they are looking to chip away at those last points of a percent of that market. And so what does that mean? That means that, weird, I shouldn't say weird, but products that they believe would help entrench them into the market or attack market segments that are traditionally held by another company, no matter how small they really were, they were willing to go after. And to me, that's where this Jordan Creek controller comes in. The Jordan Creek controller succeeded the so this is the C114, succeeded the C112. And as far as I can tell, there were some rumblings inside where Intel had worked on a successor to the C114. There was never a actual market product that came out after the Jordan Creek controller. So this was kind of the end for this particular market segment. And the reason I bring this up timeline wise is, you're looking at kind of this 2016 2017 timeline, especially for the processor that I'm going to talk about that uses this. There are many others that use this socket and controller, but the main processor I'm going to talk about is going to be the Xeon E7-8894V4, which was released in 2017, Q1 of 2017. And one of the reasons that date is going to be important is the lineup for that versus Zen 1 hitting the market. And then the other part is to give some context on, again, you're looking at almost a decade ago from the date of this recording, which is January 2nd, 2026. So, we're talking 9 years ago as far as, the numbers and scales that I'm going to talk about, which is going to help put some of this into perspective. So, just know that after this, AMD is going to surge onto the scene and going to do a reverse sweep on Intel as far as server and consumer market share. Intel is going to go from being considered untouchable to fighting for their lives over the next few years because AMD's products are going to shake the market up that badly. But at this point in time, Intel can do no wrong. So let's dive into just a little bit about why I'm talking about it, and then kind of what it is and what it's doing. So why am I talking about it? Well, a while ago, I bought a server off of eBay, which is going to be the HPE DL580 G9. And I picked up a 4 of the Intel Xeon E7-8894V4 CPUs. And when I bought the server, I really wasn't looking at it from a memory perspective. The reason being that, it has 96 DIMMs in there, but I really didn't need that scale of memory when I was buying it. I was buying it because I thought it was a viable option for a ton of PCI Express slots, along with a lot of power to back it up. So that was my idea. And again, it was also dirt cheap. That was the other real driver there was, you could get this, or you could get, other servers were easily, used servers 2 or 3 times more expensive. So this one really appealed to me in that regard, where it's like, well, is it perfect? No, but, it's also dirt cheap, so we'll give it a go. But after I bought it and I started working on it, it's like, all right, what, I'm doing the math in my head, and, the DIMM slots don't make sense. And the reason they don't make sense is because they have this Jordan Creek controller in there. And so over time, I started doing a little bit more digging, a little bit more research, and found that, it's kind of fascinating. And so I wanted to put together a video on it because I did find it this interesting. But again, it's not really relevant in this time frame, but we'll talk about why it's so impressive in comparison to today's stuff, and some of the reasons it existed. So this controller, and I'll pull up an image in a minute here, but the idea behind this controller is it takes a couple of dedicated interfaces and then provides these in a fan out array for memory. And so the way you have to look at memory, and again, I'm going to do this from a very high level perspective, is that most of the time for a given controller, for the way that memory is going to work, especially, as we've left Northbridge controllers and have moved to on package and, kind of brought the memory in, is you kind of have a way of looking where you have multiple channels. For consumer, you're going to have realistically 2 channels of memory, and then those can be broadened to, I guess the way to look at it, that is, having one and a parallel channel, so that you can have 4 sticks in total. That does not increase the bandwidth and does impact latency. And I'm going to talk about latency a lot here, insofar as you've got these sticks. And so on a consumer platform, you can have, again, I'm using consumer very loosely here, but for the last many years, consumers have usually had 2 channels, 4 total sticks. For more workstation and stuff like that, you're getting into, and again, one of the images I'm going to have in the background here is going to be from an old X58 system, which had triple channel memory, and then could have 6 sticks that expanded to 4 later on, which could have 8 in total. And that's going to be about the lineup for a very long time. Is going to be quad channel memory was where Intel kind of felt the need to stop. And so you had 8 sticks per processor, which, again, for the time gave you a lot of room, but there were applications that needed more. And it was kind of a balance because I don't, again, I say I as Intel, we're seeing this need for vastly more memory, but not seeing the need for vastly more bandwidth. Again, with some very rare exceptions on the outer fringes there, but there was a market for, massive memory needs. SAP being one and VMware being the other. And again, from an outsider looking in, VMware being the one that I feel was kind of a large driver for this product, because VMware was less sensitive to bandwidth. And again, please put an asterisk beside everything that I say, than other applications. And so when we're scaling VMware out on an enterprise grade environment where I've got hundreds or thousands of VMs that are being, put into thin clients all over the enterprise, these need more RAM than they need compute. And so this product provides that. So you go from having, uh, 4 sockets per CPU to having many DIMMs per CPU. But I'm not increasing the ability to, the memory's not going any faster. It's actually going quite a bit slower. And we are adding a ton of latency to all of this. And I think that's going to be one of the main things that's kind of interesting here is, let's pull this up here. If I can go to image. All right. So the way to look at this, and this to me is going to be a drastically oversimplified way of looking at this, but the idea here is you've got your 8894V4 CPU, which could hold 4 channels. And then I've got the C114, which is going to split out and do 12 DIMMs per C114. So Jordan Craig and C114 being the ability to show you, what each of these is. And so this gives you, kind of the fan out array that we're looking at here. And again, I picked the image in the background because I thought it was kind of fitting as we talk about this. And this was a X58 system that was kind of my first introduction into PCIe fan out. Again, fan outs being a very interesting idea where you take a controller and you have a set uplink capacity, but you need more devices than you can have on that capacity. And so you provide this switch that sits in there. Later, these would be PLX chips and many others for PCIe, but for memory, this is kind of, again, a little bit different. And so what this provides is, the way to look at this is the bandwidth going back to the CPU is not really changing. We're still looking at, I think I've got it in here somewhere. Let's see, it's a little bit further up here. Yeah, so we're looking at, 2 duplex lanes of 64 giga transfers, or sorry, 6.4 giga transfers each. So each of these lanes here, that are coming off of the V4 CPU are going to be 6.4 giga transfers. The total bandwidth that you're looking at, for 4 channels or for these Jordan Creek controllers is going to be roughly the same. And so what does that mean? That means that I've crammed a ton more sticks in here, but I've not fed it anymore. So that means that, getting data in and out of here is at the same, speed, but I have added so much more capacity to it. So again, your latency goes up quite a bit for this structure, but what it provides is, the ability to have so much more memory. Again, for the time and what this server was spec'd out at was 6 terabytes of RAM. Now, again, even for today's high-end enterprise, 6 terabytes is a pretty stout number, but 10 years ago, 6 terabytes of RAM was insane. This was genuinely pushing the envelope in ways that people had not seen. Again, it's just insane. And so what does this provide you? It provides you the ability to run these massive VMware clusters and other things like that get you these attack a very niche market. And the idea behind all of this is that we're going after a market segment, and the market shifted, the world shifted, but I think this is a piece of tech that really deserves to be remembered overall. And what does as I'm sitting here using this and working on it, what does it provide in today's functionality? And so for today's use cases, and for me and the home lab that I have here, what does this provide? And again, like I said at the beginning, I was not buying this because of these controllers and the memory, but the ability to do a couple of things were very, very interesting. One being that I could buy, at the time, before memory decided to go absolutely bonkers, memory for this server that was absolutely dirt cheap, and I could get a lot of it because memory had moved on. We were dealing with DDR5 was the primary driver for memory when I was buying the server, and it was still using DDR4, or still actually backwards compatible with DDR3 as well. But the part was you could get a bunch of low capacity DIMMs, which are not people are not very interested in anymore. As far as time has gone on, people are really only looking for the higher density DIMMs, especially on the used market. So you could get a bunch of the lower density DIMMs, say 8 gig DIMMs and stuff like that, and populate out a server for much cheaper than you could otherwise. The other interesting one is the ability to work with things like very large language models, where for a consumer, the ability to even think about running via GPU is just untenable. Being able to natively run a DeepSeek or many of the others in MIM instead of in GPU. Again, not very practical because tokens per second is almost non-existent, but it allows you to play around with things like that. The other interesting one, and one I'm considering looking at in the near future, is the ability to use it in TrueNAS. TrueNAS has an interesting function in that it has a ARC memory controller. And what that does is it utilizes memory for storage in a way that's different than your normal operating system. So TrueNAS is built around, um, data storage. It's the core premise of TrueNAS is all about data storage, and it has a feature where you can, well, natively, it will load more used data into memory for faster retrieval and stuff like that. And the reason that that is interesting is you could take a system like this, and again, if memory was not as crazy as it is currently, you could, fit this thing out with 6 terabytes of RAM, and then, allow for a much larger um, L1 arc than you would normally ever see. And so it's an interesting thought. I haven't really run it out to see if it's truly viable, but it is interesting on just as a thought and an experiment. But, you know, again, the idea here being that, it's not as relevant in today's terms, but it it does still have some benefits and some things that make it interesting as a component. I'm looking through my notes here. I did do an interesting piece here on the thermals and power draw. So again, older servers like this are not traditionally known for being very power friendly, but this does take it in a direction that I kind of found a bit astounding. And I did some number crunching, and in idle, this server consumes about 500 watts just doing nothing. It's just sitting there. It's pulling 500 watts from the wall. And so I did a little bit of digging, looking into which parts of the system were pulling that power. And I found that almost all of it, so about 400 watts, were being used by the memory controller, memory, and other memory subsystems out of about 500, which to me was kind of mind-blowing insofar as, just the idle keeping this much memory warm takes a good amount of power. You don't really think of individual DIMMs as being a power hog until you start adding this many in there. Again, they're not super power hungry, but you add 96 of them and say, again, I'm going to toss out a number that has absolutely no real world application, but say each DIMM was 1 watt a piece. That's 90 watts of just DIMM. Again, that's a made up number, but just the scale difference, in between a normal server that would have, 4 DIMMs versus this that has 96. Again, the scale out is the point that I'm trying to make. Now, the other aspect of this is, kind of take into consideration that yes, this is fairly high power draw until you turn the server and tell it to do something. And then, this will peak well over 2000 watts when it's actually running. You have a couple of MI100s in here, you're adding some CPU load on there. Yeah, you're going to blow right past and make this 400 watts of memory seem kind of irrelevant, which is, this idea behind the server and its, primary use cases. It doesn't do a lot of idle. And so, yeah, you really shouldn't, this is not a server that you want to look at as an idle grade server, I guess would be the way to take some of this data that I'm putting in here. And so, let's see here. Oh yeah, so I did do a little bit more in the to give you some perspective. And so as of the time of writing this, we have the EPYC, I'm going to call this 5th gen, so the 9005 or the Xeon 6th generation. And so these two systems have either 12 or 8 channels per CPU. And that's a thing to keep in mind here is that the EPYC systems are getting to the point where they are now at parity with a number of slots. In comparison, again, I don't know of I'm just trying to think of the servers right off the top of my head. I cannot think of a server that is a dual socket EPYC that has 48 slots per socket. I'm trying to, sorry, 48 slots total. Usually, if you have the dual socket variety, they're usually going to be just the 12 channels per socket because you're running out of physical space. Anyway, but you could bring these up to, again, 12 channels, 48 slots in total. If you had two of the double wide setups. And again, that's getting you, again, with modern DDR5 and really dense DIMMs, you're looking at 12 terabytes. The Xeon, much less. You're looking at about 4 terabytes of available capacity. And again, the other part that I want to bring up here is the form factor. And I really should have had the example. It's back behind me over there. But these memory systems existed on these cartridges that you would slide into the server. And so instead of taking up a ton of, horizontal server space, they were in these, vertical cartridges that allowed you to put just massive amounts of RAM in here and still have a functional system. These super dense, again, Xeon and EPYC systems, if you look at them, they are running out of space to put more DIMMs. And one of the, I shouldn't say issues, but one of the technical challenges that you face with a system like that is the memory sensitivity. Again, you get into latency and other things like that. Is the further I pull these DIMMs away from the CPU, I'm losing latency benefits and I'm adding penalties. And so as you push something as far away from the CPU as we had with these Jordan Creek controllers, again, it was a compromise 100%. And so far as they wanted capacity more than anything else, and this provided it. Is there anything else in there that I saw? Oh, yes, I did want to make one last note here. Again, to reiterate on the fact that I am not an engineer. I don't work at Intel. And most of the data that I have pulled up on this is, homegrown. So what I have found from the server that I own, or the little scraps of information that I have found online. So please don't view this as definitive or in any way that I am infallible. More than likely, I have oversimplified or I have glossed over stuff that other people may find very important. And so I want to put that in there. But I also want to put this out there that while I was doing the the brainstorming for this video, I fed a lot of these questions that I had into some of the AI systems that are out there, and I was pretty horrified to find that most of the data that they were pulling was just factually inaccurate. I was being told about products that didn't exist. I was being told that the Jordan Creek controller did not work with the Intel V4 line of processors. There was so much misinformation out there. So I wanted to create real content, not AI generated content, that, you know, kind of addresses some of these concerns that, I see as this piece of technology kind of fades into obscurity. And again, does it really matter? No, nobody uses it anymore, but I think it is something that is worth remembering. Um, there's a, a YouTube creator, the history guy, that I really enjoy. And one of his taglines is history that deserves to be remembered. And I kept having that thought come up when I'm looking at this, and, kind of the ideas behind it is, this is almost technology that deserves to be remembered. It's, kind of a high watermark for Intel and a really interesting application. And it's kind of sad to see that there's not a lot of data out there for it. So again, this will probably be my least viewed video of all time, but if nothing else, I did want to create it, and with that, I will sign off.